Imagine standing on the observation deck of a super-tall skyscraper, looking out at the city below, completely unaware that the ground is miles away and the very room you are standing in is moving. It sounds like the plot of a disaster movie, but the truth is, if your skyscraper didn't sway in the wind, it would likely snap in half. We tend to think of buildings as rigid, unyielding monoliths of concrete and steel, but in the world of structural engineering, rigidity is actually the enemy of survival. When Mother Nature unleashes hurricane-force winds or seismic shockwaves, a building that refuses to bend will eventually break. To understand how engineers outsmart some of the most violent forces on Earth, we have to look past the shiny glass facades and dive deep into the fascinating physics of how skyscrapers are engineered to sway, flex, and ultimately survive. To understand the problem, you have to look at what wind actually does to a tall building. As wind blows against a skyscraper, it doesn't just hit it and stop. It creates a high-pressure zone on the windward side and a low-pressure vortex on the leeward side. This creates a phenomenon known as vortex shedding, where swirling eddies of air pull the building from side to side in a rhythmic, repeating pattern. If the frequency of these wind gusts matches the natural vibrational frequency of the building, you get resonance. This is the exact same principle that caused the famous Tacoma Narrows Bridge to twist apart in 1940. If a skyscraper is too stiff, the shear stress at the base will accumulate until the materials fail. Therefore, engineers design skyscrapers to be surprisingly flexible. Modern towers are essentially giant, vertical cantilevered beams designed to absorb and distribute kinetic energy rather than fight it head-on. Of course, bending is only half the battle. If a building sways too far, or too quickly, it creates another major issue: human motion sickness. Even if the structural steel is in no danger of failing, office workers and residents on the upper floors will feel violently ill if the building oscillates too aggressively. This is where advanced damping systems come into play, acting as the invisible shock absorbers of the sky. The most famous example of this is the tuned mass damper, like the massive 660-ton pendulum suspended near the top of Taipei 101. When a gust of wind pushes the tower to the left, the massive steel ball inside lags behind due to inertia, and then swings to the right, counteracting the building's movement and bleeding off the kinetic energy before it can build into a dangerous oscillation. Beyond swinging pendulums, the secret to skyscraper survival is hidden right in the materials and the structural skeleton itself. Engineers use a combination of ultra-high-strength concrete and structural steel frameworks that are specifically designed for ductility. Ductility is a material's ability to deform under tensile stress without shattering. Think of it like a paperclip: you can bend it back and forth a few times before it breaks, whereas a piece of cast iron will snap immediately. Furthermore, many modern supertalls feature open-air mechanical floors or aerodynamic shapes, like rounded corners and tapered profiles, which literally trick the wind into flowing smoothly around the building rather than catching it like a massive sail. It is a brilliant blend of aerodynamics, material science, and physics. Ultimately, skyscrapers are not monuments to human stubbornness, they are monuments to our understanding of nature. By accepting that we cannot stop the wind or the earth from moving, engineers learn to dance with them instead. The next time you look up at a towering giant piercing the clouds, remember that its ability to sway in the breeze isn't a flaw, it's the exact reason it's still standing. If you found this deep dive into engineering fascinating, hit that subscribe button and ring the bell so you never miss another look at the hidden physics shaping our world.